All right, guys, let's take a seat. All right, yesterday we were exploring some connections, not necessarily connections, but we were just exploring, getting a feel for what an exponential function looks like, what an exponential graph looks like, and remember our ultimate goal is to be able to relate the two together. That way, if I give you a graph, you can write the equation, and if I give you an equation, you can write the graph. Okay, our ultimate goal. Through our exploration yesterday, we were looking at different properties related to what the equation is, what the graph is, and I let you guys just kind of do a free-for-all, okay, just looking at whatever characteristic first popped out at you for those graphs or equations. Today, though, we're going to take a look at the same 12 graphs. So on page 302, these are the same cards that you had yesterday. But I want us to try to find one more characteristic that we may not have really touched on yesterday. Okay, and we're going to take a look at this characteristic a little bit more today. So with these 12 graphs, I'm going to tell you that 7 of them have something in common and the other 5 have something in common. I want you to try to find those 7 and those 5 and think about what that commonality is. So unlike yesterday where you got to choose a grouping, I'm now telling you a grouping and want you to figure out what they have in common. Okay, so 7 of these and 5 of these should go together. Try to find them. Anybody think they got it? Were you able to group 7 and 5 separately? I don't want to put any pressure on us, but I was under the assumption that there's only one way you can group 7 and 5 separately. The other class actually found 3 ways to do it. So I'm curious if we can kind of pick apart. Is there any way you can group 7 and 5 separately? Did you find one, Matt? Yeah.
7 of the graphs, as they approach negative infinity, they get closer to the horizontal asymptote.
Okay, so as you approach negative infinity, which direction are you moving in?
You move in to the left.
To the left. Okay, so as you go to the left, you approach a horizontal asymptote. So that would be this one, this one, this one, this one, this one, this one, and this one. That looks like 7. Notice how on the left-hand side it's getting closer to an asymptote. So that means the other 5, as you go to the left, you do not approach an asymptote. Bless you. Looks good. I like that one. Are there any other ones? I find this rather fascinating because this is the one that the other class was not able to get. I was able to kind of like pry it out of them, but they found the other two that I did not notice initially. So I find it interesting that you find this one first, or at least Matt found this one first. Are there any other ways that we can break up 7 and 5? It's okay if you can't get it. Like I said, I was surprised they were able to find the other ones. This was the main one I was hoping we'd get. All right, so we'll talk about this in a moment. The other ways you can break up 7 and 5, just so happens, is if you look at the intercepts. So notice how 1 has a positive x-intercept, or sorry, positive y-intercept, and 4 does, and 6 does, and 7 does, and 12 does. I think those are your 5. And then all the other ones have a negative y-intercept. Okay? And the x-intercepts just so happen to work out the same way. Okay, so there's other ways you can group 7 and 5, but this was the main one I wanted to look at. What we're going to do is looking at these graphs, I'm going to try to zoom out a little bit more. Depending on the direction in which you approach an asymptote, we can actually classify the graph as a particular term, and that's either growth or decay. Do those sound familiar for exponential functions if we've dealt with them in the past? Okay, so we're officially going to define what exponential growth means and what exponential decay means. Matt kind of approached it from a different end. He said as you go to the left, whether you approach the asymptote or not, by definition, we're actually going to move to the right. So we're just going to look at the other side of the graph. So looking at my red ones, notice how as I go to the right, my graph either goes up forever or down forever, depending on what the shape actually is. That's what's classified as growth, because you're going to increase or decrease forever. There's like no bound to your graph. So exponential growth is when we move away from a horizontal asymptote to the right. So all my red graphs would actually be classified as growth. If you look at the decay ones, okay, the blue graphs, as you move to the right, notice how you approach an asymptote. Okay, so you are not increasing or decreasing without bound, bless you. You're kind of reaching some, bless you, you're kind of reaching some limit or some value in the end. So decay graphs move toward a horizontal asymptote to the right. Okay, so those would be all of our blue graphs. Now, in addition to growth and decay, we can actually get even more specific. So, for instance, if you take a look at 5 compared to 8, okay, they're both blue graphs, so they're both decay. But as you trace the graph, notice how number 5, your pencil goes down as you trace it, whereas number 8, your pencil goes up as you trace it. So we can classify decay as either increasing or decreasing, depending on the direction of the graph. So 5, we would say, is an example of decreasing decay. So we know our pencil is going down, but as we go down to the right, we're approaching an asymptote. Okay, we're being very specific on the shape of the graph. For 8, since our pencil is going up, we would classify this as increasing decay. We can actually classify growth in the same manner. So if we look at the red ones, for instance, bless you, for instance 9 and 12, notice how as I trace 9, my pencil goes up. So this graph is increasing. And since my pencil goes up away from an asymptote, this would be growth. For 12, my pencil goes down, so this would be decreasing. And since my pencil goes down away from an asymptote, this would also be growth. Okay? So depending on the shape of the graph, you can have increasing and decreasing, growth or decay. As I was walking around yesterday when you were making your little pairings from the cards, some of you actually grouped them this way. You had 4 different groups, and I think some of you asked if you could do that, and I said no, just try to make 2. But I'm pretty sure some of us noticed the different shapes of the graphs yesterday. Is that a fair assumption when you were trying to classify them? That's a good thing. Okay, so what we're going to do today is a little bit more exploration, trying to draw those connections between what the equation looks like and what the graph looks like. So for here, we're just working on some terminology like growth, decay, increasing and decreasing. We're eventually going to relate that to the equation. So on the next page, okay, keep these graphs handy because we're going to have to look at them. But on the next page, we're going to focus a little bit more on that equation part. We did some of this yesterday when we were just piecing together like what each number means in terms of the spot in the equation. Do we remember what the A value represented in our exponential form? Good, Olivia? That's your leading coefficient, okay? What did the B stand for in the equation? Yeah?
Base.
That's your base, okay? And what did this D stand for? If it's a number all by itself on the end, yeah? That's your constant. Okay? So actually each one of these letters, I know we haven't really talked about the C yet, but we'll get there eventually. Each one of these letters is actually telling us something about the way the exponential graph should look. And we're going to start to explore those connections. So I want to focus on A and D, at least for now, and we'll eventually get to B. So when we look back at these graphs, maybe on the left-hand side, let's go ahead and label what A and D are for each one of these. All right, so A is the leading coefficient, the number in front of the base. Remember, the base will never be negative. So if you have a negative in front of the base, that's actually your leading coefficient. So A is the leading coefficient, D is the constant on the end. If we look at number 1, our leading coefficient would be 1, the number in front of the base of 2, and then our constant number is the plus 1 on the end. All right, so go through all the different graphs, label the A and the D, and then we're going to try to find a pattern between the A value, the D value, and how it kind of relates to the graph. So I don't know if you noticed as you're labeling or not, but the A value always seemed to be 1 or -1. Did you notice that? Okay. That's just because we're dealing with kind of introductory, simple exponential equations. It could be something else. Like it could be a half. It could be -4. Okay, it's not always just going to be 1 or -1. but there is something related to this value that relates it back to the graph. So just don't get it set in your mind that it's always going to be 1 or -1. Okay, it could be something different. So looking at all of our numbers here, can we maybe find a connection between maybe the A value and the graph, or what the D value is in the graph? Can we find a pattern? See something, Blake? Yeah. I like it. Okay, so that's actually one of the characteristics that you noticed yesterday, right? Didn't we write down some of the graphs were above the asymptote, other ones were below? So if we take a look at this, 1, 2, 3, 4, 5, 6, and 7 all had an A value of 1. Notice how they're all above the horizontal asymptote. The moment you get to 8, which had an A value of -1, it's now below. So it seems like if the A value is positive, you're going to be above the asymptote, but if it's negative, you're going to be below. Okay, so we're going to make note of that little connection. So on page 303, let's look at the value of A. We said this represents our leading coefficient. If A is positive, we're going to write our connection down, and if A is negative, we'll write our connection down. All right, so for numbers 1 through 7, A was positive, and we said the graph was above the horizontal asymptote. The moment we got to 8, though, which had a negative A value, the graph was below the horizontal asymptote. So now we're starting to just be able to look at an equation and start to picture what the graph is going to look like in our head. So if we can identify what the leading coefficient is, we now know something about the picture of the graph. Is it above the horizontal asymptote or is it below? Okay, we're going to start to look at different values because the more information we can pick apart from the equation, the more accurate the graph or the picture is going to be in our head. All right, let's try to look at our D value. This was our constant term on the end. Can you find a connection between the D value and what the graph looks like? Yeah? That's our horizontal asymptote. Did we mention that yesterday? Okay, so we got a little bit ahead right there. So notice how D is the location of that horizontal asymptote. So we kind of have 3 different cases as to what the D number could be. D could be positive. D could be negative. And what if D is 0? Like you don't have that constant term. All right, so if D is telling us the location of the horizontal asymptote, what do we know if D is positive? Can we describe where that horizontal asymptote would be located on a graph? Maybe we'll take a look at our graphs. So here was 1, here was 2, here's 1, and 2. Okay. What do all those horizontal asymptotes have in common? They're all positive, but where are they located? Can you give a description? Yeah? They're above the x-axis. If you have a horizontal asymptote that's depicting a y value that's positive, you're above the x-axis. So if D is positive, we have a horizontal asymptote above the x-axis. Similarly, if D is negative, our horizontal asymptote is below the x-axis. What if we don't have a constant? What if our D is 0? Where's the horizontal asymptote? On the x-axis. Good. Awesome. Okay, so we kind of did a lot so far, and we're kind of only halfway through the class. We've discussed growth, we've discussed decay, we've gone over increasing growth, decreasing decay, okay, those different kind of combinations, and now we're starting to think about how the equation is related to the graph in terms of its different numbers and where they're located. Let's see if we can take this a step further and kind of relate even more characteristics together. So on the next page, okay, we're still going to look at the same 12 graphs. What I want us to do, and I know we did it a little bit earlier, is go back to that growth or decay description, but also the increasing and decreasing part. So these first two columns are actually going to give us descriptions as to what the graph looks like. In the last two columns, we're going to pay a little bit more close attention to the equation. Okay, again, we're trying to make connections or patterns between the two, so we want to compare them. The last two columns, we're going to look back at those reflections that we discussed yesterday. Okay, if we have a negative somewhere, what does that tell us? And now, instead of focusing on the leading coefficient or the constant term, I want us to look at the base value a little bit more. So we're officially going to describe the base as either bigger than 1 or in between 0 and 1. Okay, notice how the base is never going to be negative, so that's why we're kind of stopping at 0 there. Okay, we can't go into negative numbers. All right, so we'll do the first one together, and then I'll see how we do with the rest of them. If we look at number 1, maybe I'll erase some of my markings. Okay, as you trace the graph, notice how your pencil is going up the entire time, so we can classify that as increasing. If you look at the graph even more, notice how on the right-hand side, the graph is going away from the horizontal asymptote. So that's our classification of growth. So we would say number 1 is an increasing growth exponential function. So now, instead of looking at the graph, let's look at the equation a little bit more. Do we notice any negatives that we should account for? Are we flipping the graph in either way? I'd say no, okay, because we don't have a negative out front and we don't have a negative in the power spot like we saw yesterday. So there's no flips for this graph. What's our base value? What's being raised to a power? Can we tell based off the equation? 2, okay, and 2 is definitely bigger than 1, so we'll say our base is bigger than 1. Do you guys think you can go through the other 11? I think you can. Okay, go ahead and try them out. First 2 columns are analyzing the graph, second 2 columns analyzing the equation. See how you do. If you wanted to rewrite it, you could.
So, what this thing would be, the equation is zero
It would be b is, with the way it is written right now, it would be 0. But if you rewrite it, that's actually going to change, right? Because that's going to change the reflection, which we're going to talk about a little bit tomorrow. The b is
class is 40 minutes. This class has 13 minutes left. 40 plus 13. Just say B is less than 1. I know, that's why it's like zero, that just means that the time is forward. Yours is fine. Number 4. I did not use
All right, let's check these out. We're going to kind of do rapid fire like we did yesterday. So if I call your name, you're going to do 2 of them. Okay, you're either going to do both graph boxes or both equation boxes. Okay, we're just going to go through, see how quickly we can get through this. Alicia, can you do our graph boxes for number 2? Okay, and Hadley, can you do the equation ones? Okay, so if it's less than 1, it's between 0 and 1. Good. Okay. How do we do for 2? Good. All right. Number 3. Julia, can you do graph? Decrease and decay. All right. And Mason, can you do our equations?
No, for based on if there's a reflection in that it's less than
In between 0 and 1. Looks good. How do we do on 3? Good. All right. 4. Logan, can you do our graph? Increasing growth. All right. Jack, can you do our equations? No negatives. Okay, so none. What'd you say, sorry?
Less than 1. Less than 1.
B's between 0 and 1? Let's see. Okay, this one could be tricky. It is a fraction, right? So you might think between 0 and 1, but 3 over 2 is bigger than 1. It's 1.5. Okay, so it can be tricky because I know it's a fraction, but you gotta look at the value of the fraction. Okay, bigger than 1. How do we do on 4? Good. All right, 5. Carter, could you do our graph? 5. Okay. Decrease and decay. Looks good. Noah, our equations. In between 0 and 1. How about 5? Good. All right. Blair, graphs for 6.
Increasing and growth.
Increasing and growth. All right. And Robbie, could you do our equations?
9 and then
B is greater than 1. How do we do on 6? Perfect. All right. Lincoln, graphs for 7.
decrease and decay.
Decrease, decay. He says with authority. Good. Matt, our equations.
Y-axis flip and then B is greater than 1.
B is greater than 1. Okay, so we're starting to see some negatives show up in the equation. As I was walking around, I noticed how some of you wrote down like yes or no in this column, which I guess answers the question. But can you maybe be specific? And if you said yes, write down the type, because we're eventually going to try to make a connection or relationship to the type of reflection. Okay? 7 looks good. Blake, can you do 8 for the graphs? Increase, decay. All right. And Grace, can you do the equations?
X-axis reflection, and then it's
In between 0 and 1. All right. Looks good. Maggie, can you do graphs for 9?
increase growth.
Increase growth. Okay. And River, equations?
Y-axis and
Greater than 1. Looks good. All right. Travis, 10 for graphs.
increase growth.
Looks good. Lizzie, could you do our equations for 10? B is greater than 1. All right. Did we have a reflection somewhere? It's okay. X-axis. Perfect. All right. Erica, graphs for 11. Increase in growth. Perfect. Olivia, our equations. In between 0 and 1 looks good. All right, Elsie, graphs for 12. And growth. Okay. And Lainey, you're going to end things with us with the equations.
X-axis and
B is greater than 1. How do we do? Perfect. Okay, tomorrow we're going to take a look at this chart a little bit more in depth to see if we can make any more connections between the way the equation looks and what the graph should look like.
So I have an entire Wikipedia page